Hello! The title of my webinar today is Recent DC Arc Flash Research and its Impact on ETAP Methods and Solutions. My name is Albert Maraquin, and I am the Vice President of the Electrical Safety and Dynamics Engineering Division here at ETAP. I have been performing research and development on ETAP DC Arc Flash products for over a decade. And today, I would like to share the webinar spotlight with one of my engineers in the Arc Flash team. His name is Raghu Viragavan, who's here with me today and will help me to demo some of the capabilities of ETAP 20 relating to DC Arc Flash analysis. Of course, he'll do that after I get a chance to introduce the concepts on the current research on DC Arc Flash and its impact on the current way we, as electrical engineers, analyze or calculate DC arc flash incident energy. My webinars are always created with the intent of sharing knowledge that we as safety professionals acquired through the research and attendance of different conferences and seminars. The purpose of this webinar today is to bring out to light the trend or direction that the industry has taken when it comes to the DC arc flash analysis methods. About a decade ago, there was no published methods, and there was a big need for having some kind of methodology so that we could perform DC arc flash analysis. My colleague, Dan Doan, an IEEE fellow, and others published a series of papers on the use of the maximum power method as it applies to DC arc flash. Well, this has served the industry very well, and I gotta give a lot of credit to Dan Doan and others who presented papers of this. They provided a means for DC arc flash to be evaluated in its early stages. Well, however, after having the opportunity to do some more research, and the time that has passed has allowed other organizations to come over and perform some actual tests, it has come to light that the maximum power method as applied to DC arc flash analysis is overly conservative in a lot of cases. So just like its counterpart, the maximum power or Ralph-Lee method in IEEE 1584-2018, this method will have to be superseded and new methods have to be used that will give us more accurate and less overly conservative results. So in this webinar, I will focus on how DC arc flash is calculated for photovoltaic systems, and I will try to explain why the methods we have in ETAP are very accurate for estimating the DC arc flash incident energy for the majority of systems that are available for commercial, industrial, and renewable energy systems. At the same time, I will let my colleague Raghu, as I mentioned before, explain some of the new methods and tools in ETAP 20 during the demo of the software, and how those tools help us apply the methods that ETAP DC arc flash has available for different types of systems. It is very important for us to be able to apply the right method to the right type of system. I guess that after we go through this webinar, I hope that you can take home the knowledge on how inaccurate some of our current DC arc flash calculation methods have been and how overly conservative those results may be. And I hope that you can take home with you how we can apply or configure ETAP DC arc flash options to provide the most accurate results based on your type of DC power system. These are some of the organizations who have recently published research findings and tests, actual tests, laboratory tests on DC arc flash. As I will show in the next few minutes, their findings and conclusions all agree. However, before we proceed to see what their findings and conclusions are from these actual test observations, I would like to share the same findings I had and actually presented at the Electrical Safety Workshop in Louisville, Kentucky in 2015. Unfortunately, at that conference, I was unable to present due to personal reasons, and my colleague John Francis from ETAP was able to present this method on my behalf. The method was presented during a tutorial, and in fact, it arrived at the proper conclusions, which are very similar to the conclusions that these organizations have found during their actual tests. Unfortunately, at the time, the method presented was not backed by any real tests. So the assumptions of the method as it was presented on this tutorial could not be validated. And thus, the maximum power method as applied to photovoltaic system, since it is actually the most conservative or absolutely most conservative answer that we can have, gained track and became very popular. Of course, as engineers, we always want to provide the most conservative result and not make a prediction that is less conservative than the actual result. Now, after all these years, and after different organizations have had the budget and opportunity to perform tests, now the industry as a whole is trying to correct the direction the industry took at the time. And yes, this has become a challenge. And unless we have a new DC arc flash standard, or we take a new direction when it comes to the NFPA and IEEE research collaboration, we may not be able to shift this direction the industry has taken. So hopefully, after we go through this webinar, we can see how these new methods can give us a far more accurate estimation of the incident energy. So here is the concept that was presented in 2015. The high-level equivalent system representation that is shown in this slide of a DC power circuit tells us that for a shunt DC arc flash event, the amount of power that is delivered by the arc is proportional to the arc current and arc voltage. The arc voltage, of course, is dependent on the voltage drop across the anode and cathode, plus the voltage drop across the arc column. The length of the arc column can be empirically estimated as a function of the conductor material and the gap between conductors. The dynamics of the arc as it ignites and extinguishes are hard to capture and thus are typically neglected for most arc flash models. In fact, in the development of the new IEEE 1584 AC arc flash model, we decided to neglect the arc ignition and extinction phases in the development of the model. So, going back to DC arc flash, the task at hand is to find a relationship that defines the arc resistance once the arc stabilizes, or basically after it has ignited and has become an actual arc event. Of course, there are various equations available, several researchers have provided equations that help us represent the arc resistance as a function of the arc current and voltage. As a function of the arc current and gap. The Stokes and Openlander empirical method equations have proven to be some of the most conservative at representing this relationship, yet fairly accurate under most circumstances. In the previous slide, we saw that a high-level representation of the equivalent DC power circuit for a voltage behind impedance type of source. However, since we're discussing photovoltaic systems with an emphasis on that particular system, and as I explained during the 2015 electrical safety workshop, the photovoltaic system short circuit characteristics are nonlinear, and for a high portion of the operating region behave almost as constant current sources. The operating voltage of the photovoltaic system is also influenced by a controller, which is typically not shown in here or in most diagrams, or in particular in high-level equivalent systems. The maximum power point tracker or controller biases the operating voltage towards the maximum power delivery point. However, this only occurs during normal operating conditions as the voltage of the photovoltaic system nears the rated inverter operating voltage. Under arc flash or short circuit conditions, the effect of the maximum point tracker controller is actually negligible, and the short circuit current is ruled by the irradiance IV or PV curves for the panel. It is perhaps here where the big or greatest mistake was made in assuming that the DC arc flash in photovoltaic systems operates under this knee point or the maximum power point. And this causes the results to be overly conservative. To assume that the photovoltaic system operates constantly at the maximum power point during an actual arc flash event is not the correct way of looking at this. To summarize this slide, we can see that the stability point of the arc resistance and current can only be established can only be established by a set of multiple iterations on both the IV curves and the nonlinear Stokes and open-landed arc current and gap conditions. In other words, both the arc resistance and current have to be solved iteratively, and at the same time we must determine where this arc stabilization point lies on the IV or short circuit curve characteristics of our panels. The simulation results presented at the Electrical Safety Workshop in 2015 showed that it was very likely that the arc voltage was going to lie in the majority of cases or settle at a relatively low voltage portion of the IV curves of the panel. Consistently, in the model simulations results that I observed from the method that I developed, we saw that the arc voltage was about 30 to 40% of the maximum power point voltage. The resistance of the cables and connectors along the way is almost negligible, but is still considered. With this simulation capability, I proceeded to use this method to calculate the incident energy of our ETAP corporate office solar system. We are blessed with the fact that we have an actual solar system on which we can actually monitor and observe different DC renewable energy behaviors. This simulation method that was created as part of ETAP software more than 8 years ago was presented at this electrical safety conference. Let's take a look at the 400 kilowatt photovoltaic system in ETAP. But before we do that, I'd just like to reemphasize that the actual test results and observations from the laboratory tests that have been performed by several organizations over the last couple of years have proven that, in fact, the arc voltage developed in a DC PV, DC photovoltaic system when in the presence of an arc actually does lie in the region highlighted by these red arrows in this particular slide. Here's an image of the photovoltaic system that was built in our corporate building. The capacity is about 400 kilowatts after all the panels. This image shows the system under construction. The schematic diagram reveals that there are a total of 5 combiner boxes and 1 inverter cabinet. As we can see, all the single inverter cabinet where all these combiners feed the DC current to. The simulation that was performed using this software was performed for 2 different arc flash analysis, one on the combiners and one fault at the inverter box. So our first fault will be location 1, which is one of the combiners, and our second fault will be at the inverter box, which is the second location. Here are some images on the combiner boxes locations that are scattered through the parking lot facility in our corporate building. The enclosure size is about 20 inch by 20 inch with a depth of 8 inches. Here's a peek inside the combiner boxes along with the protective devices, which are protective fuses. In this case, the protective fuses, as it is likely in most photovoltaic systems, are in fact not expected to operate in the event of an arc flash or an arc, DC arc, anywhere on this system, but are here just basically to protect the cables from other types of overloads. This is typical for these photovoltaic systems, and so in other words, the overcurrent protected devices are expected to take a very, very long time to operate, if they do operate at all. The inverter cabinet showing here on this image, both on the left side where we have the incoming wires from the combiner boxes, and on the right hand side where we have the input to the inverter. In this case, we can do an arc flash analysis on the DC side, on the left hand side, and we're going to neglect on this particular webinar the calculation on the AC side, which would be the output of the inverter. We'll leave that for a future webinar. Here in this particular slide, we have a high-level representation or diagram of the photovoltaic system that shows the 2 locations that were faulted. One of the combiner boxes and the actual inverter cabinet, as I showed on the previous images. So, at the time the results were presented, these are the actual simulation results from the software as were presented at the Electrical Safety Workshop in 2015. It was found that for our relatively small 400 kilowatt photovoltaic system, that the most popular methods, which are max power down-down and max power published by Enrique et al. And other authors, actually predicted nearly 6.5 to 7 calories per centimeter square at the inverter location. This of course, is just the DC side of the cabinet, as I mentioned before. The AC part of the analysis is less, as I mentioned before, I would like to leave that for a future webinar discussion. It's not included in this slide. The conclusion is that at the time that this incident energy is over-predicted by a factor of 6 times at least. The over-prediction is expected to get worse as the size of the photovoltaic collector system increases. For a 1 megawatt or higher collector system, the prediction using the max power method, as explained by these two methods in row 1 and row 2, can easily exceed the 40 calories per centimeter square range. But in fact, for those systems using this method, the actual result is more likely to be in the 5 to 8 calorie range. Bottom line, for our 400 kilowatt photovoltaic system, our method predicted about 1.4 to 1.6 calories per centimeter square, which is about 6 times less than what is predicted with these other methods. So at the time, the method that we had in ETAP, as I mentioned before, showed very accurate results, but yes, still they were conservative. However, as with any method, there was a need for validation. As I mentioned, we lacked the actual laboratory test results to back up the assumptions. Fortunately, last year at the Electrical Safety Workshop in 2019, the following results were published, which started to back the findings of the method that I first published 6 years ago. The incident energy overestimation using the available maximum power methods for photovoltaic systems, which had become popular over the last 8 years, show that the incident energy is overestimated by a factor of 6 to 10 times. This confirms the simulation results of the method that we put in ETAP about 8 years ago. Another organization, again, also performed laboratory tests, in this case EPRI. The test results showed that the same findings and conclusions that we had already seen from the National Renewable Energy Labs. The Stokes and Openlander method results are produced by ETAP, as shown in this slide. The closest yet conservative results to the actual test results. For the 1 megawatt photovoltaic array that they used to test, the measured results were in the range of 2.5 calories per centimeter square. And the Stokes and Openlander results, using the double iterated method that we have available in ETAP software, produce about 3.5 calories per centimeter square. The remaining methods, as published in the references that I showed earlier, are off by 6 to 10 times, as can be seen in this slide. In other words, the ETAP results are shown with the light gray column bars. The actual measurement results are shown with the soft blue color bars, and the actual over prediction is from the Enrique et al. And Dan Doan methods, shown in the yellow bars and the dark blue bars. It is clearly obvious that the results are overestimated by several magnitude factors. So now let's watch an actual event or an actual incident of an arc flash in a solar or photovoltaic plant. A 1 megawatt photovoltaic array feeds the collector system in what seems to be a particularly cloudy day. What can be observed from this video is more of an arc, and this is an interesting point. There's a difference between an arc and an arc flash event, and we will discuss that in the next section of videos. This is a very interesting video because it validates a lot of the initial assumptions in the calculation. For example, it is not expected for the overcurrent protection to trip, and this is obvious. This arc continues to arc and sputter for a long time. The 2-second rule is often used to estimate such events, and it's very likely that you will end up using that in your actual calculations. Similarly, we can see that the photovoltaic system is a significant fire hazard, and thus DC arc fault detecting relays and equipment has been now mandated by code requirements by the NEC for certain rooftop installations where this could cause a fire or instantiate a fire. Note that at least for this fault, it does not seem that the energy produced is actually a significant ionization of the material and ionization of the air materials around the arc. There doesn't seem to be a significant size plasma cloud or molecular cloud generated. Well, to summarize this, the current doesn't seem to be high enough to provide a severe level of ionization energy that is required to generate what we actually call an arc flash, such as an event that we would get in a low voltage or medium voltage industrial size switchgear. Okay, now that we've observed what the energy level and the type of arcs that we get in a photovoltaic system, and now that we know that we have available methods that can allow us to get a far more accurate estimation of the incident energy, yet still conservative, we can now change our gears and look at other types of DC arc flash tests. Now we need to discuss how it fares, how this new DC arc flash arena fares in terms of high energy DC power systems, where the fault currents actually reach levels as high as 20,000 amps or higher. These are some of the organizations, as shown in this slide, who have recently published results of the research from laboratory test conditions on DC arc flash tests. I would like to personally thank Kirk and Simon at Hydro-Quebec for providing the footage of some of the higher incident energy or higher current DC arc flash events that we'll see in the next few slides. Bottom line, this slide serves us as a transition point between the lower energy photovoltaic systems, which are ruled by the nonlinear characteristics and current limitations of photovoltaic panels, into the world of high current battery power, converter power DC systems, where the amounts of currents are 10 to 20 times higher than we see on these photovoltaic systems. Before we continue to watch some of the videos that I have prepared for you guys today, I'd like to continue the discussion on higher energy DC arc flash events. And to continue the discussion, it is actually necessary for us to introduce the concept of the electrode configurations which are applicable in these situations. For photovoltaic systems, the vertical conductor in the box and vertical conductor in the box terminating in an insulating barrier configurations are actually likely. In particular, the BCBB configuration is very likely, as shown in this middle image in this particular slide, and it is very likely to occur in tightly packed conductor areas or where the conductors run very near to the enclosure wall, such as in combiner or recombiner boxes. In fact, there are differences in the results when the enclosure itself serves a path for current return. This was actually proven in several of the photovoltaic systems performed by these organizations. The configuration on the far right is less likely in photovoltaic systems, and it's not tested as much for photovoltaic systems. So bottom line, to summarize the slide, we can confer that as we develop further models, in fact, the electrode configuration concept that we have from the AC world, or IEEE 1584 2018 world, will also come into the picture in DC arc flash analysis. So hopefully over the next few months or couple of years, we can develop a model that takes into account this electrode configuration selection. However, a very common test used in laboratory conditions for high current DC arc flash tests is the butted electrode configuration. The fact that the electrode gaps can be easily adjusted or controlled makes this a very preferable configuration for single phase AC and also DC arc flash tests. As we will see in the next few slides and videos, there may be some additional considerations which need to be applied when applying this butted electrode configuration. However, that is really not the focus of the current discussion. We are trying to see how higher arc current DC arcs produce significant amounts of incident energy, and how the calculation methods available in ETAP can help us to calculate more accurate results. The first test is for a 7.8 kiloamp available DC short circuit voltaic current configuration or system. The gap, initial gap in this system, of course, the gap will grow depending on the erosion rate of the electrodes or the copper butted electrodes that we have inside this box. So the initial gap is 6 millimeters. The incident energy measure is about 1.7 calories per centimeter square. The amount of short circuit current is about 8 times more than what was available in the previous photovoltaic arc flash events videos that we saw. The current is high enough to generate immediate shrapnel, a molecular and plasma clouds, and other effects like high ionization of the molecules around the air environment around this arc. The voltage is lower than that of the previous photovoltaic system by at least a factor of 3 times, being around 140 volts DC. So, in conclusion, it is not the voltage that has a significant impact, but it is the actual amount of short circuit current and the gap of this particular test event. As we can see, the gap has grown from 6 millimeter to over an inch because of the arc erosion caused by the shrapnel and the ionization of the conductor material. Let's look at the results for arcs of similar nature. Here we can see that the incident energy from this particular test, which is 7267, just around the middle of our particular chart in this region here, 7267. This is the test that we're looking at. Okay. Here we can see that the ETAP, Stokes and Oppenlander method, produce around the simulation predicts about 3.5 calories per centimeter square. Okay. We can see that the Hydro-Quebec or actual test, laboratory test, predicts an energy around 1.9, 1.8 calories per centimeter square. And the incident energy prediction using the maximum power method predicts approximately 9 calories or 8 calories per centimeter square. This again shows that the overprediction is in the factor of 6 to 10 times. So our ETAP result is conservative, yet not overly conservative by a factor of 6 times. This is what we can conclude from this particular test with 8,000 amps of DC short circuit current available. Now let's look at another video for where we can see a different condition. This is a test that was set up with now a higher voltage, approximately 260 volts DC, and a much higher current. In this case, we have 20,000 amps of available DC short circuit. Notice that we can observe almost twice as much the shrapnel and also erosion of the actual copper conductors. The duration of this test is about 750 milliseconds. As we can see, the erosion rate of the conductors is significantly higher, and also the amount of shrapnel and incident energy increased significantly. This, of course, is a factor of the higher short circuit current that we have available. For this next video, which is the last video on this family of high energy videos that I have prepared for you today, we'll have an available DC short circuit current of 20,000 amps and a duration of 2 seconds. This is actually more than twice the arc duration of the previous DC arc fault event from the video that we saw a second ago. The total incident energy that was recorded from this test actually exceeded 40 calories per centimeter square. Wow, that's a lot of sputtering. Pretty much all the conductor material was eroded away inside the box, and this pretty much converted into ionized copper oxide particles along with ionization of nitrogen and oxygen, which release a tremendous amount of heat. Okay, so after we've seen this test, now we can look at the results. Of course, we don't have time to go through every test, but we can actually go and look how we fared through the majority of tests. In the case of the previous test, the actual test we have, we're looking at simulation results for tests 72575 and 7279. So we're looking at 7275, which is right here, the first test, and 7279, which is the big, lots of current, lots of time test. So focusing only on test 7279, we can see that the ETAP result is within a fraction of a calorie difference. Of course, this is done with one adjustment that we must take into consideration. And for that adjustment, I would like you guys to consult with ETAP technical support or myself so I can explain how we need to adjust the methods or apply the options so that we can get this kind of accuracy on the simulation. We can also see that the prediction of the maximum power method is approximately 140 calories per centimeter square, when the actual measured incident energy is only 40 calories per centimeter square. So I would classify, as can be seen in this slide, high energy arcs as an arc that occurs in any circuit which can sustain approximately 15 to 20,000 amps or more of voltage full current. This is very important because arcs with lower currents than that are not going to have such a severe ionization and plasma cloud phenomena, which are the causes of most of the heat transfer towards the electrical worker. So after reaching this point, and after seeing all these videos, and after showing you the charts of the results, I think that you guys get the picture of how much we're overly estimating the incident energy and how much more accurate of estimations we can use if we apply the methods that we have had in ETAP for actually almost 8 years. With this, I would like to pass the baton to my colleague Raghu Veeraraghavan, who will take us through the actual demo of the DC arc flash module in ETAP 20.
Thanks, Albert, for your presentation. Hello, everybody. This is Raghu Veeraraghavan, and I'm excited to demonstrate DC arc flash analysis with ETAP, starting from modeling to analyzing the outcomes based on the selection of methods and techniques for different applications addressed in the previous session respectively. In addition, you'll be going through some of the key and useful features implemented in ETAP 20 version that may be beneficial to you. Let us start with PV panels and understand its modeling in this project. Each PV panel consists of several PV arrays, and ETAP provides a built-in library for PV panels from different manufacturers embedded with PV and IV curves respectively. It also lets you to customize the data and add your own library to the same. It is important to build your panel based on adding PV arrays in series or in parallel. So the number of PV panels added in series directly impacts the voltage of this particular PV panel. In other words, adding PV panels in series increase the voltage of this PV panel, and the best practice is to make sure the voltage from the PV array in total match the nominal voltage of the collector bus that it's connected to. Adding PV panels in parallel increases the current contribution from the PV arrays, and it can be summarized in the corresponding short circuit page of the same panel. Once this is done, the next step is to model the combiner box fed from these PV panels through a collector cable, as shown in this picture. The DC collector systems or combiner boxes can be modeled in the bus editor, starting with the nominal voltage in DC and then the corresponding arc flash parameters listed in the equipment properties section. Here, the user could enter the height, width, and the depth of the box along with the gap between the conductors and electrodes, and enter the working distance in the arc flash page respectively. ETAP automatically populates the shock protection boundaries based on the corresponding nominal voltage entered in the info page according to the NFPA 70E tables. Now that we entered the required data to perform the analysis, it's time to switch to the DC short circuit mode and run the corresponding short circuit analysis for the combiner box and the DC panel respectively. And this magnitude of the current is calculated based on all the PV arrays combined and fed into the combiner box and the inverter cabinet on the DC side of the inverter. Now, it is time for us to switch to the DC arc flash mode and establish the two separate study cases, with each study case referring to the maximum power method and the Stokes method respectively. To begin with, let us first run the maximum power method case and observe the results on the DC collect 1 and the DC panel respectively. Maximum power method calculation for the DC combiner box, which in this case the DC collect 1, is summarized in the bus arc flash page. The total incident energy calculated in this location for a given working distance is based on the operating time of the source protective device DCF3, which is operating at 0.243 kiloamps that is seen in the source path. This can be visually shown in a time current curve in ETAP using the star menu. For that purposes, I have created a star view that shows the manufacturer curve of DCF3 that is connected to the combiner box for this fault location. As you can see, the current is actually 243 amps, which could obviously result in a longer clearing time. Starting from ETAP 20, we have enhanced the program to show this source PD arcing current on the time current curve by enabling this calculated / user defined source protective device option for a given bus nominal voltage. And this clearly indicates that the total current seen by this particular protective device can obviously operate for a longer clearing time and hence cause a very high incident energy. In this case, the program still limits the clearing time to 2 seconds to avoid a high incident energy accumulation, and it is actually configured in the study case options as shown here. Similarly, the DC panel has its source protective device DCF2, and that can also be visually shown in another star view that I have created for the same project. The source PD arcing current in this particular location is actually in the order of 700 amps, that is actually clearing time around 4 to 5 seconds basically. Now that we understood the current and the operating time based on the maximum power method for these faulted location, let us move on to the next method listed in this project, which is nothing but the Stokes and Oppenlander method along with a double iterative technique that Albert has mentioned in the previous slides. Let us run the Stokes method and use the arc flash analyzer to compare the differences between the results for the same locations and analyze the reason behind the reduction in the incident energy and how it is justified based on the short circuit characteristics of the sources in this project. So the concept of calculating the short circuit current for PV arrays comes down to a point where they are mainly dependent on the IV characteristics provided by the manufacturer and the irradiance calculation that occurs in a particular time zone. And also, based on the Albert slides here, the arcing current calculation would be based on the low voltage portion of the IV curves, which is actually provided in this diagram. So approximately the arc voltage will be in the ballpark of 30 to 40% of its rated PV array voltage though. So the arc current calculated based on the Stokes method plus the nonlinear IV curves provided in this project is the concept of the double iteration method, which is far more accurate than the actual IBF and the I-arc relation from the maximum power method. In other words, the power released by the arc as a function of the voltage drop across the arc and the current, not based on the actual open circuit voltage of the system and the current. And this voltage drop across the arc in the Stokes method is actually the function of the gap between the conductors that is calculated using the test results performed by Stokes and Oppenlander for copper and aluminum electrodes. And it is for the same reason the max power method for higher voltages could give you a very high incident energy, or in lower voltages could give a very lower arcing current that causes a higher incident energy due to a longer clearing time. Whereas the Stokes method with the double iterative technique would be more useful in giving the right estimate of the incident energy compared to the maximum power method. Based on the concept discussed on the double iteration technique, let us go take a look at the DC panel location and examine the actual arc current results for Stokes and Oppenlander method, and then compare it against the actual time current curves and see how the arc current calculation and resulted in a quicker clearing time compared to the maximum power method. As you can see, the final results from the Stokes and Oppenlander method using the double iteration technique has given a higher arcing current to deal with, which could obviously give a faster operating time in this particular condition. The overconservatism of the maximum power method can still be projected in this case by removing the 2-second rule. So for the same DC panel location, the Stokes method still remains the same on the fault clearing time even after removing the 2-second rule. The arc flash analyzer can still show the selected elements from the one-line diagram to filter out the results on the panel as seen here. Now the maximum power method with the 2-second rule removed originally gives you the overly conservative energy based on the actual operating time of the fuse DCF2. So the original reduction is actually from 12.57 calories to almost 0.14 calories per centimeter square for a given working distance for the same set of parameters that was given as input to the DC cabinets of the inverter side. Now, the choice of the maximum power method and the Stokes method comes down to the actual available incident energy results and the available PPE that is used for the current location, and the choice of the method involves a good engineering judgment to choose between one or the other, and in most cases the Stokes and Oppenlander method with double iteration technique could be more ideal for a application that involves PV arrays and photovoltaic systems. To switch to another application, which is involving a combination of voltage behind impedance or constant current sources in a commercial facility or involving batteries and chargers, and to see how ETAP calculates incident energy for multiple source systems. And also we will witness the new ease of use enhancements and the deliverables enhancements that was made in ETAP 20 for DC arc flash. This project is an example of another application which involves contribution of chargers or rectifiers to a DC system that is backed up by batteries with different modeling options and techniques. These sources have been enhanced, and the scope of this session will demonstrate the modeling of these enhanced sources from a short circuit point of view, and also the use of different configurations and determine the incident energy calculation based on the worst case scenario. This example also includes the calculation of incident energy per stage until the last protective device has completely, and then continue with the modeling strategy plus the scenarios that are used in this project, and then determine the arc flash incident energy result at DC bus 2. The modeling of DC chargers in ETAP 20. The DC chargers are modeled as a voltage-dependent current source that inject current to the system based on its bus terminal voltage. The rating page of the DC charger comprises of the voltage and the full load amps and the corresponding maximum and the minimum voltage limit specified accordingly. The short circuit page, however, explains the contribution of the short circuit current to the system depending upon its terminal voltage and the corresponding voltage percentage depending upon the location of the fault. To demonstrate the actual contribution of the charger, it is important to fault a bus at a time and examine the terminal voltage of DC bus 1 to which the charger 2 is connected to. So let us choose the configuration with all the sources in and start to fault at DC bus 1 where the actual short circuit terminal voltage is 0. And as you can see, the charger does contribute 150% of its rated current as the short circuit current to this particular faulted bus where the terminal voltage is 0. Now as we move further away from the charger as a source to the downstream, the terminal voltage at DC bus 1 starts to increase based on the user-defined short circuit curve as shown in here. So when the bus 2 is faulted, the actual contribution of the chargers is based on 1.79% of the bus terminal voltage, which in this case is in between the ISC minimum and ISC maximum. Towards a farther location from the charger, the terminal voltage starts to increase and the corresponding short circuit current is injected to the system. This can be again witnessed that the actual VSC max and the V operating minimum, the corresponding short circuit current, resides in between this curve region. Further moving downstream, it reaches to a point where it exceeds the V operating max of the charger, and which in turn shuts off the charger contribution for the following faulted location. And as you can see, for the given short circuit terminal voltage, which is actually greater than the VOP max, there is no more short circuit current that is injected to the system. The battery sources in ETAP 20 has been enhanced to account for either a voltage behind resistance or to comply with IEEE standard 946. The state of charge and discharge is also tapped using the ETAP library built in for batteries depending upon the manufacturer and the charger characteristics, whether if it is a lead acid or a lithium ion battery respectively. This can be visualized in the library selection, where a user could either have the corresponding parameters estimated or used a standard value. For example, the rate of charge and discharge curves based on the voltage can be manually or estimated using this library parameter estimation regarding the battery parameter estimation and the battery energy storage system enhancements in ETAP 20. Please refer to the website for the related webinar associated with the same. The battery sources and the charger sources, the modeling option could be either used based on an individual charger contribution from the editor settings or a global setting that is used for batteries or chargers correspondingly and configured in the short circuit study case. With that, let us move on to our original scope on evaluating the arc flash incident energy at bus 2 depending upon several configurations and the source's contribution to the faulted location. In this project, I have created 3 different configurations, starting based on the normal configuration where the utility is feeding the system on the DC side through a rectifier or a charger in the same condition where the batteries are assumed to be in the charging mode. The state of discharge starts when the battery system energy storage is starting to release energy when a loss of utility condition has occurred. And there is the third configuration where both sources are set to be online and the incident energy evaluation is performed accordingly. To begin with, I have created 3 different scenarios based on different configurations that I just explained and evaluate the incident energy based on each configuration. So the scenario number 1 explains the incident energy calculation based on the contribution of the utility and the chargers only. So we do have 2 charger contribution, one from the charger 1 on the utility U1 and the charger 2 from the utility U2, based on the fact that the batteries are out of service, or in other words, in charging mode. The scenario number 2 actually deals with the loss of utility condition, where the contribution is primarily from the battery sources only. In this case, we do have protective devices that operate based on the actual sequence of which the current seen by the protective device and the trip time is calculated. And as per the third scenario, where both the utility charger and the battery system are in service, that could actually calculate the incident energy for the given time frame, having the proper sequence of operation starting from DCCB3, which operates first, DCCB6, which operates second, and DCCB1, which operates third, respectively. Upon finishing this particular condition, in ETAP 20, we have introduced a new concept of calculating the incident energy, accounting based on the de-energization of the source from its corresponding source protective device sequence of operation. Or in other words, ETAP now has the ability to calculate the incident energy per stage depending upon the sequence of protective device that de-energizes each source path of a fault. For example, in this condition, ETAP can calculate the incident energy at DC bus 2, accounting for the removal of incident energy from each source after the corresponding protective device has de-energized the circuit. To enable this feature, the study case method tab is used. And I have created a new study case that says DC arc flash underscore with subtraction with the Apply Incident Energy Subtraction option selected. Now I made a separate scenario which is called the scenario number 4, which is considering the both online source configuration, which is considered to be the highest incident energy or the worst case, and to see the account of the subtraction included in this particular scenario. Upon running the calculation with subtraction, you can notice the reduction of the incident energy from a category 4 or a level 4 to a level 2 respectively. The sequence of operation of events depending upon the time at which each source path is de-energized can be visually documented or seen from the report database. Upon clicking the report database under the subtraction report, the following sequence of operation table is created for users to examine the stage-by-stage calculation of incident energy from the point of initiation of the fault until the last protective device has operated. In this example, as you can see, the first protective device that cleared the fault coming from battery 1 and battery 2 is acknowledged to be DCCB3. So from 0 to this particular time, which is 0.009 seconds, it is assumed that the total bus fault current is used in the incident energy calculation, which is around 6.15 kiloamps. Now, as we move on to the second stage, where the DCCB3 contribution is cut off, the remaining stage from FCT1, which is the fault clearing time 1 to fault clearing time 2, at which DC circuit breaker 6 operates, the incident energy calculation involves only the two sources that are still active, which is the charger number 2 and the other contribution from the combination of batteries in the charger 2. So at this accumulation of incident energy, ETAP reduces the total arcing current with the reduction in the sources coming from battery 1 and 2 removed. And in the third stage, from fault clearing time 2 to 3, it is assumed that the contribution from the charger alone is added to the incident energy calculation, which in turn constitute to the third stage of the incident energy. And at the end, all the incident energy calculations that are calculated per stage is added to give the final incident energy value at a given working distance and the last protective device clearing time. Now that we explained this stage-by-stage calculation, it is time for us to analyze all the scenarios using the arc flash analyzer again. Now, as you can see in the arc flash analyzer, the original condition, the worst case incident energy, happens when there is no subtraction, which is actually in the both online configuration, where you could see the calculation of the fault current and the incident energy is calculated to be higher when both sources contribute to the fault. Whereas, depending upon the logical implementation of the subtraction method, it is possible to eliminate that particular report, considering the fact that each source gets de-energized after the corresponding fault clearing time is calculated from the de-energizing source protective device. We can compare the three different scenarios with the subtraction and then determine the incident energy calculation with the subtraction mode on and consider which gives the worst case scenario. And once the worst case scenario is achieved based on the both online configuration, ETAP has the capability to display the worst case incident energy in ETAP one-line diagram with the help of data blocks, which is introduced in ETAP 20 version. To show the one-line diagram, with the worst case incident energy from the arc flash analyzer, simply go to the update data block option and enable the data block toolbar in the one line diagram, so that the moment you hit on the update data block toolbar, the incident energy gets updated for the worst case based on the selected reports from the arc flash analyzer. With this, the user can also export the one line diagram with the worst case scenario, eliminating the result that is overly conservative without taking the account of de-energizing each source by its protective device. ETAP also supports another deliverable using the standard and the custom labels, which can be generated after running all the possible configurations and scenarios and still determine the worst case incident energy that can happen in this particular fault location each stage. Used as a sticker depending upon proper engineering judgment that is being made, and also accounting for without even setting it up in ETAP projects. And we introduced a new concept in the arc flash calculator, up with a new batch process that was included in ETAP 20. So with this batch process, a user can simply import an Excel spreadsheet and have the ability to start selecting as many rows of faulted locations with several current, voltage, gap, and different working distances, along with a fault clearing time and different arc flash boundary values or the electrical break open threshold, and select several methods based on open air or enclosed equipment, and do a quick batch process to explain what incident energy calculations would differ depending upon the different input data has been given. So before running the import process and the export process, you can notice here that the Excel sheet is blank, and once the import process is complete, the user can simply run a calculate button and process as many batch entries as they want, and still evaluate the working condition and the final incident energy based on each working distances and the corresponding arc flash boundary accordingly. This tool will be very useful to do a preliminary arc flash study before even setting up all the scenarios in ETAP 20, and it is also very powerful to determine the combination of several methods that could be used from the standalone calculator that is available in ETAP. ETAP also has the flexibility to account for a quick calculator that could easily provide an incident energy evaluation depending upon varying any of the system parameters or the corresponding fault clearing time respectively. With that, as a summary, I would like to conclude that we have learned a lot of new key features and techniques that would help a user to perform an arc flash study in the DC world and enhance the calculated results and the choice of the right methods, and use the powerful capabilities of scenarios and wizards and other ETAP add-ons that could make the incident energy calculations much more accurate. My presentation, and have Albert take over.
So thank you, Raghu, for that presentation. Thanks for showing us all the features in ETAP 20. So in order to summarize our webinar today, we can say that as we can observe, the industry is starting to rectify the direction in which the methods which are recommended for use in DC arc flash are selected. Testing is ongoing, and surely everyone will interpret the results differently and come out with different partial methods developed based on partial testing. And of course, in order to really get a formal answer or a formal unifying way of doing DCR flash analysis, it is my humble opinion that we need to start a similar standard like IEEE 1584-2018 that will unite or coalesce all the DCR flash calculation methods. Hopefully, we can continue the education process and eventually reach consensus on a single method. For now, we have seen that when properly configured, ETAP results have excellent correlation with test results. However, I would encourage the study engineer to contact ETAP to establish a discussion on what parameters to use for each type of system. In the world of DCR flash, in reality, I would say that 80% of the accuracy is in the actual estimation of the volted DC short circuit current, and the remaining 20% is actually in the equations that we use to estimate the DCR current, resistance, and incident energy. The modeling algorithm needs to account for the different types of sources. Like Raghu showed in his presentation, ETAP not only produces accurate results, but also has very nice features and tools to save analysis time and to help us deliver the results to the end consumer of an arc flash analysis. Thank you very much for watching, and hopefully you can join us in future DC arc flash related topic webinars.